G'day friends, and welcome back to our channel. In the last couple of episodes we shared how our bore well was drilled and how we set up a bore pump to tap into this precious resource. And of course, after finding water, our first question was, can we drink it? And to figure out what our water could be used for, we sent a sample to our local Department of Primary Industries for a lab analysis. So this video will be all about using a water testing kit, interpreting the lab results, and understanding how the properties of water are affected by the concentration of various naturally occurring minerals. We'll talk about the challenges that can arise from using bore water and take a look at some of the solutions that are available for common water quality issues.
Okay, so today we're going to be testing our bore water finally, which we're very excited about. Fingers crossed we're going to be able to drink it. So there's many different places you can get testing kits from. This one is from the Department of Primary Industries, or DPI, which is the government, which is a really handy, cheap way to do it. We'll provide a link to the website. Basically they post you out this little testing kit, which if you open it up, you get a little bottle to put your sample into. So they say on the back in the instructions here, which we'll put up on the screen, to rinse the bottle in the test water first, and then to fill up the bottle with no air gaps at all, and then keep it refrigerated until you can drop it off or post it back to them for testing. Okay, and then in here there's also a form to list out what you're testing for, all of your personal details and things like that, which we'll also put on the screen.
And these here are the tests that we selected. They included the new bore characterization and also the drinking water routine chemistry test. And because both of these options included the standard test, we weren't charged for it twice. So the cost was pretty affordable, just $166.
So, also on here, it mentions 4 different scenarios. We're doing a bore, so it says that we need to run this for at least half an hour before we collect a sample, which we've definitely done that here. So we're ready to grab a sample. Okay, so first we're going to rinse the bottle. And then we'll fill it up and make sure there's no air bubbles. So it's like full. And we'll screw on the lid. And then we'll have to put this into the fridge until we go into town tomorrow and drop it off. And we'll let you know what the results are.
G'day, welcome back to our channel, and for this part of the video we're inside with our laptop taking a look at the bore water test results. So interestingly, to begin answering the question of drinkability, this was one of the easier things to determine, simply because our bodies are really good at processing the minerals that naturally occur in natural bodies of water. And when it comes to issues such as potential E. coli contamination and other bacteria, this is only really something that occurs due to human-induced pollution, like for example if there was a lot of livestock nearby and the waste from that livestock interacted with the bore water somehow. But that is something that's really difficult to test for, simply because one day you might test your water and it shows up as clear, and the next day you're in a toilet with a sore stomach after drinking water that was supposedly good to drink. So it does have an unpredictable nature from basically what we found out from the testing place. But in our instance, it's very unlikely that there's going to be an E. coli infection, simply because our bore has been drilled more than 30 meters deep. It's underneath bedrock and we don't really have livestock nearby. So that part should be all good. And so as a basic answer, yes, our water is drinkable. But the challenging part was figuring out how our bore water can affect our soil, plants, and the plumbing that we use inside the household and for irrigation. Because for instance, hard bore water is not shown to be harmful for humans. In fact, the minerals found in hard bore water, if anything, are beneficial to supplement our own nutrient intake, because it's calcium and magnesium, very valuable nutrients. But when it comes to plumbing, hard bore water can end up leaving a scale deposit, which over time ends up blocking plumbing. So that's an issue to do with plumbing, but hard bore water is more than okay for humans to drink, from what studies have shown over many years. And so while this isn't going to be one of the most fun off-grid city couple videos, water quality is a really important topic to understand so that we can anticipate and prevent costly problems before they occur. And even though, funny enough, like with everything out here, we thought this would be an easy and straightforward topic to understand, I ended up spending days doing online research, and after that I still had questions, and so we got in touch with the Department of Primary Industries where we did the testing, and we also had to get in touch with an agronomist from the local land services, because some of the questions that I had about our bore water, I simply couldn't find the answers for online. So there's a lot of good information here to cover. We're going to talk about all of the different things that we tested for in the water, the potential issues that can arise if those things are out of balance, and some of the solutions that are available out there to deal with those problems. So let's get stuck into it. Alright, so now taking a look at the actual water test results, this is going to be a great example for what you guys might expect to see if you ever end up carrying out some water testing for yourself. So we got 4 attachments in total from the Department of Primary Industries. This is attachment number 1, and it lists all of the different parameters that were tested for. LOR is the limitation of results, which basically explains how precise the testing was. We've got the different units that all of these things are measured in, and finally we've got the results for our specific bore water sample. The next attachment includes a number of different parameters within which the water is considered suitable for drinking, irrigation, or livestock. And the most interesting thing about this document is that you'll see there's a little asterisk over here next to most of the parameters related to drinkability. And if we scroll down the page, what we find is that what the asterisk means is that it's a recommended level, not directly health related, but relates to the aesthetic quality of the water only. So that's what I meant in the beginning when I was talking about determining the drinkability being the easy part. So this document lists all of these parameters as taste specific as opposed to health related, which is an interesting feature that we'll talk about later. But moving on in these attachments, next up, what we've got is a guide for how to interpret all of these results, and it covers these key features here, such as pH, alkalinity, hardness, and so on. And the next attachment was one that DPI, Department of Primary Industries, kindly prepared for us, which is basically a summary of all of the attachments that I showed you so far, specifically related to our sample of the water. So for instance, pH over here is said to be satisfactory for most plants, stock uses. It's within the Australian water drinking guidelines, and if you're someone who doesn't like too much detail, this is an attachment that you can view to see everything that you can use your water for. But the challenge arises if any of the levels of elements in your water exceed the recommended guidelines. Like for example here we've got chloride that's a little bit elevated, the turbidity exceeds the requirements, and we've got a couple of other challenges as well. So this is where you might want to take a further look into what all of these things mean, and that's basically what I spent a fair bit of time understanding to prepare this information for you guys, so that hopefully it doesn't take as long for you to process. And so the cool thing about this information is that this document here was also sent as an Excel file, and so we were able to summarize all of those attachments to one page. And so this is our beautiful spreadsheet here that we'll be using to understand what all of these different parameters mean. We're not going to go into too much depth, but we're going to get a pretty good preliminary understanding of how all of these different features can affect your bore water and what you might be in for in terms of managing potential issues. Alright, so now taking a look at the first item on our list, we've got the pH of the water. So bear with me, there's a few notes to cover here. I'm not a chemist by profession, so these notes are going to be needed so I don't miss anything. So what we've got here is that the pH of the water should be between 5 and 8. If it's outside of those limits, that's a reason to investigate further and see what's going on with the water, is there contaminants and whatnot. But to understand the nature of acidic and alkaline water, we've got the different descriptions here. So acidic water can corrode metal pipes, affects plant growth through nutritional problems, and can change the acidity of the soil if the pH is really low. And it also can reduce the effectiveness of herbicides and pesticides. Now, while acidic water can corrode metal pipes, what alkaline water does is it precipitates the calcium and other minerals in the water into solids. Now what that does is clog pipes. It can result in blockages in plumbing, so that's also no good. What we want is for the water to be as neutral as possible. And now, while an imbalance in the pH is likely to indicate an issue, it's not the sole factor contributing to the corrosive or scaling nature of the water on plumbing. That is something that's going to be covered later on in the calcium carbonate saturation index. So we'll talk about that later on, but just keep in mind that all of the items here that have a different color, the way they're highlighted, all of these factors here contribute towards this saturation index, and that's ultimately what's going to determine whether our plumbing is going to have issues from the bore water that we're using. So now, there's a different kind of test of pH compared to alkalinity, because these are two different things, which once again doesn't make things any more simple. But for the purpose of item number 1, pH is a simple test to see whether the water is acidic or alkaline, and the test is done with just pH drops. But do note that there's no health requirements for drinking bore water in terms of pH, because dangerous levels of acidity are unlikely to occur in nature. However, we may have all heard that alkaline water is known to be more beneficial for our health than acidic water. Now, these parameters are sourced from the World Health Organization, because I saw that Australian drinking water standards referenced the World Health Organization, so I decided to go straight to the source and to find out what they have to say about the acidity of water and how that relates to health. So now, keeping in mind that bore water is expected to be between a pH of 5 and 8, and just for comparison's sake, if we take a look at how acidic, for example, Coca-Cola is, what we find is that it has a pH of 2.6 to 2.7. So comparing that to a already problematic bore water with a pH of 5, what we can see is that that's more than 100 times more acidic than our bore water if we're drinking Coca-Cola. So that's what these guidelines mean by the fact that these parameters aren't necessarily health related, because our body has an amazing ability to buffer pH. And now pH is measured in pH units, and the results for us were 7.2, which is about as close to neutral as you can get. So in that sense, we lucked out and our pH is good to go. So next up, we've got alkalinity. And now alkalinity is not to be confused with pH, even though that sounds confusing. What alkalinity is the water's ability, basically, to resist changes in pH. So looking at the definitions here, alkalinity is measured using pH strips, as opposed to the drops that are used to measure pH. And these strips determine the presence of carbonates and bicarbonates through chemical buffering. The buffering is something that's referred to as the water's ability to resist changes to pH. Moderate alkalinity is good because it means that our water is more resilient to change in pH. And now alkalinity is also not a sole contributor to any problems per se, but rather a metric used to determine the calcium carbonate saturation index. So for our intents and purposes, we're not going to focus too much on the alkalinity figure here, because that is something that contributes to other metrics. So the next item to talk about is salinity. And salinity is one of the most common and most annoying problems to deal with, because salt is really difficult to remove from bore water. So to understand salinity, we've actually got two types of measurements here. And the first one is electrical conductivity. And what the conductivity of the water indicates is the concentration of soluble salts by measuring the concentration of ions. So the unit of measurement here is microsiemens, and it's roughly the same as 680 milligrams per liter total dissolved solids. So if you take a look at the next item, it's total dissolved solids, and they're both measuring the same thing, but they do so using different units of measurement. Simply because when you're talking about salinity, most commonly you're going to be talking about it in terms of milligrams per liter or parts per million. Now that's determined using the total dissolved solids figure of milligrams per liter. But to begin to understand the effect of salinity on the different uses for our bore water, we basically have to realize that if we've got 1 million liters of water and our salinity, let's say, is 680 milligrams per liter, that's 680 kilograms of salt that are present in 1 million liters of water. And now what salt does is it affects plant growth. However, different types of salts have different effects on plant growth. So we explore that a little bit later on when we look at the content of chloride. But for now, just know that there's also no definitive health guidelines for salinity in drinking water because natural bore water reserves are simply unlikely to exceed safe drinking limits. But with that said, when you go above 1000 parts per million, the water does become unpalatable. That's as stated by the World Health Organization. But once again, to put things into perspective, the content of salt in the ocean is 35,000 parts per million, and that's not related to our 890 microsiemens, that's related to our 600 milligrams per liter. So the other comparison is that human urine has about 2000 parts per million. So if we pull up the calculator really quick, and we've got 20,000 here divided by our 600, we can see that our water is 33 times less salty than urine. So once again, this is one of those things that has an asterisk next to it, and in terms of drinking water guidelines, humans can tolerate quite an impressive amount of salt. And in fact, salt is healthy for us. It helps with vital bodily functions and whatnot. But not the same goes for our soil and plants, because salinity can accumulate in the soil and damage plants and whatnot. So salinity is one of those things where I've got a guideline here that says basically when you grow above 2,500 microsiemens per centimeter, that's when you start to really have problems with different crop growths and buildup of salinity in your soil. But once again, that's something that's case specific because different plants have different sensitivities to salts, and if you've got a salt problem, that requires to be explored in more detail in your own time. So next up, we're continuing on this whole topic of salinity, and we've got chloride here. Now chloride would have already been included in the salinity figures, but it's listed here separately because chloride is a type of salt that tends to burn the leaves of plants. And here we can see that above the level of 175 parts per million, it begins to affect plants. And ours is 170, which is just below that. So once again, we just lucked out. And looking at our overall salinity figures, we can see that the guidelines say that 900 microsiemens is the limit, and we're at 890. So when we drink our bore water, we can taste a little bit of salinity in it, but it's something that we have gotten used to and it doesn't matter at all. So once again, we're good in terms of salinity, and let's move on to the next mineral. So next up, we've got calcium and magnesium. So they're very similar minerals, and they're also types of salts. So calcium over here and magnesium are the main contributors to water hardness, and excess calcium specifically is one of the minerals that builds up scale in plumbing. There are no irrigation guidelines for calcium alone because its effects can be offset by pH, salinity, and alkalinity, and that's once again something that we talk more about in this calcium carbonate saturation index. But just know that the presence of calcium is good for plants. It's a very valuable mineral, but if it's out of balance with these other parameters, then it can start to be a problem. Similarly, magnesium is also one of the two key contributors to water hardness, and it can also build up a scale in plumbing. But the funny thing about magnesium is if there's too much of it, you can find yourself on the toilet experiencing laxative effects. So in that sense, nature has a sense of humor. So once again, there are no drinking water guidelines because magnesium and calcium are both naturally occurring minerals that are very likely to exceed healthy levels for drinking water in nature. And now that we've covered both calcium and magnesium, these are the two minerals that can help us to understand the hardness of our bore water. So the hardness of bore water is a measure of the calcium and magnesium present. And while these are also salts and also classified as minerals that would have been included in those salinity results that we looked at earlier, hardness is something that's specific to calcium and magnesium salts only. Hard water can reduce the effectiveness of soap, and it can block pipes due to that calcium and magnesium encrustation. However, if you have really soft water, it can also be even more corrosive because calcium buildup to an extent protects metal surfaces as well. So this is a tricky one. You want your water to be in the middle once again. And note that there are also no drinking guidelines for hard water, but if that magnesium content is high, it can have laxative effects. But that said, it's unlikely. Hard water is so far proven to be good for us because calcium and magnesium are really beneficial elements for our dietary intake. So we've covered a few things so far, and now we've arrived at the calcium carbonate saturation index, which is basically a ratio that takes into account all of the things that we covered so far. So I'll have the formula for the calcium carbonate saturation index on the screen pop up if you're curious to learn about it. It's also known as the Langelier saturation index. Langelier came up with it in the 1930s, which is pretty impressive because it's 2024 and I still struggle to understand it almost 100 years later. So what the Langelier saturation index, or the LSI, does is it measures the balance of our water. So this balance is calculated through, as mentioned, the pH, the salinity of the water, and the alkalinity and hardness, where negative values on the LSI scale are corrosive, but positive values are scale forming. So it's not enough to look at all of the previous things to figure out whether our pipes are going to corrode or have scale in them. We have to take a look at the calcium carbonate saturation index to know exactly the effects that our water will have on our pipes. So note once again, there's no drinking water guidelines for the LSI index. This is something that is going to have more effect on our plumbing than our health. However, the health impacts of the LSI index are more likely to be indirect. If, for example, our pipes are being corroded and there's extra metals like copper in the water, now that can affect our health. But it's not the pH, alkalinity and salinity and whatnot that's going to affect us per se. It's the indirect effects that that has on our plumbing and other things, like, for example, chlorine becomes less effective when the Langelier index is too high or too low, and then obviously if the water is not disinfected, then that can cause hygiene issues. Once again, indirect. So our bore has a ratio of negative 0.5, which is just on the cusp of starting to be corrosive to the pipes, but the risk of that is slight because it's not an extreme number. Next up, we move on to an element called sodium. And now sodium is a type of salt, but what we learnt about calcium and magnesium previously is that it's also a type of salt, but the thing about calcium and magnesium is that their effect on the soil is the opposite to that of sodium. Now what calcium and magnesium do is they flock the soil together, which is really good for the structural properties of the soil and for drainage and whatnot. Soil is good when it's flocked, but what sodium does is it makes clay particles in soil disperse. And now sodium is a really troublesome thing, and it's actually something that we've got a problem with, in that the sodium concentration is much higher than calcium and magnesium. And what that can do is the sodium can bind with the clay particles in our soil. Binding means that you can't wash it out with water. It's going to accumulate in the soil and potentially cause problems. However, in terms of drinking, there are no health-related drinking water guidelines for sodium in water because, once again, it's unlikely to exceed naturally healthy limits for us. But I went and had a look for the Australian health guidelines, and it basically mentioned that as an adult, 2,000 milligrams per day is the absolute upper limit for the sodium that you should be taking in, and for newborns that's 400 milligrams per day. Now, to show you the resource that we used, It's basically here, it's Health Direct, which is an Australian government website, and for the different age groups, it's got the different sodium intake limits there. So taking a look at our results here, we've got 150 milligrams per liter of sodium, and let's say I was really thirsty today and I drank 4 liters of water. That's 600 milligrams of sodium, and that doesn't even begin to reach the daily limit. So once again, we're all good in this sense. And now, sodium absorption ratio is something that is a bit of a scary problem to encounter. If you've got high levels of sodium in your water, what that can do is have very detrimental effects on the soil by making it impermeable to water, resulting in reduced vegetation growth. But the most severe risk of all is the destabilization of soil structure. And this happens when soils with a high clay content become dispersive, meaning that they can be easily washed away by water. This presents serious erosion problems and destabilization of the soil structural properties. So that's something we'll talk more about in the managing water quality problems section in this video. But just to show you a quick picture of what Sodicity can look like, it's quite scary. So you can see in this picture here, all of the soil got washed away. And this is something that happened at a mining site where the soil was disturbed and sodium basically came through from the groundwater and prevented vegetation from being able to stabilize the soil, and as a result there was pretty serious issues that had to be addressed. So this issue is something that I researched in depth because this is a risk for us to happen if we use our sodic water to irrigate crops. So I'll explain that in more detail later, and in the meantime we are basically wrapping up our understanding of all of the different types of things that we tested for in our bore water. The only thing really left is turbidity, and that is once again just how murky the water is from clay and soil particles and whatnot. And once again, there's an asterisk there, meaning that you can drink murky water, that's okay. Soil is where our food is grown. Soil is essentially made out of the same stuff that we're made out of, so it's not problematic. But our figure of turbidity is shown to be quite high, and that was actually something that was an indirect result of the high iron content. And now the reason our water became turbid was because of the iron in the water oxidizing. So if you see some of the pictures of our bore water coming out straight from the source, it's basically crystal clear. But something that really stumped us is that even though our water was really clear when it first came out of the pump, with time it began to turn orange, and at first we had no idea what was going on. We were really concerned, but what we ended up figuring out is that basically the iron content was so high that it was oxidizing in the water, and it started to clog our shower very quickly on, and we basically had to figure out a solution to remove some of the iron from the water before we could use it for household purposes. Also, as part of figuring out the iron problem, we experimented with adding bleach and hydrogen peroxide to the water, because at first we weren't sure if the water was changing color due to algae or some other kind of issue. But the rapid change in color to an orange shade resembled the oxidizing nature of iron. And this is really a key summary of everything that you can expect to have in a water quality test. Because these things were a little bit complicated to explain, they're all interrelated and they all cause different issues. But as you go down the list, all of these other items here are basically, they're either taste specific or they're poisonous. If you've got too much arsenic in your water, it's definitely not good, and you don't need to combine that with any other metrics. You simply know that if you've got arsenic in your water, that's no good, you're in trouble. Same goes for the rest of these elements here. And now, if we take a look at our specific results for these dangerous items, we can see that our result was, for example, for arsenic 0.05, but to be able to drink the water, it needs to be 0.01. And this is something that is a limitation of the test. So basically this test was not precise enough to let us know if there's 0.01 milligrams per liter of arsenic. And that's where we scroll down to the dissolved nature of the elements, and this is a test that's more precise, which you can see the limitation of results here is 0.00005, and now something that was flagged as alarming potentially in our results here. If we take a look at it again in the more precise test, we can see that we have 0.0004 milligrams per liter of arsenic, which is all good. So if you're looking at these general figures and something seems a little bit elevated, don't be too alarmed. This is something that can be viewed more precisely later on down in the test. So now, in talking about some of the solutions that are available out there, if you've got problems with your bore water quality or wherever you're sourcing water from, if you have elevated levels of any kind of element that's resulting in problems, we're going to be covering the most common solutions to most common problems. And for the sake of following the structure of the features that we covered so far, pH is one of the problems that's the most easy to fix. And we've got a quick article here just to check out from the New South Wales government, in that pH is something that's easily adjusted by adding an acid or alkaline substance to the water supply. And there's also filters out there that can interact with your water and basically change the pH in that way. But coming back again to our sequence of things that were tested for, we've got salinity here, and this is actually one of the most serious, annoying, and difficult to deal with problems out there. Now, the reason that's the case is because salt is actually not something that can be removed by a filter, because salt is dissolved in the water. So normally the only way to get rid of salt effectively is through reverse osmosis. So if your water is too salty to use for irrigation, that is a really unfortunate problem. And if somebody does find themselves in such a situation, the Department of Primary Industries has a document dedicated specifically to dealing with saline bore water. So reverse osmosis is explained in this document, and just to keep things brief here, these are some diagrams for how reverse osmosis works. Instead of the water being pulled towards a more saline solution like happens in nature through osmosis, it's pushed through a membrane. So then what you have left is water that is really nice for use, but you have basically an equal part of salty water. And not only are the systems expensive for doing reverse osmosis on a large scale, but you're also left with a waste product which is called brine, salty water, and that's required to be disposed of really thoughtfully. Like, for example, if you plant a crop that can specifically use salt water like saltbush, that is one way that farms can still use their saline bore water. But it really is an unfortunate situation. So if you find yourself in this situation, there's plenty of information out there for what the salinity limits are for livestock and for different crops that you might be growing. And this document also takes you through how much you might be expecting to pay for a system that's going to treat your bore water, and how much electricity is required, which you can see that if the water is brackish, you need 1.5 to 5 kilowatts of power, which is a lot of power basically. And there's different parameters here for waste. We won't get into that in too much detail, but just for some rough figures, what you got here is that if you want 10,000 liters of potable water per day, the cost could be about $21,000 for a filtration system. So that's what I meant when I referring to this problem as basically being the worst one that you can have if your water is too salty to use for irrigation. But if we take a look at water hardness, that is once again a problem that's relatively easy to deal with. So what we've got is some technologies here that we're looking at, and water softeners start at around $2,500, and they're pretty bulky. They require maintenance and they require you to top up the salt and whatnot. But good thing is that there is a newer invention, which is instead of a water softener, there is a type of device called a water conditioner. And as you can see, instead of costing thousands, it only costs a few $100s, and it lasts for a pretty long time. And the way it works is, instead of the minerals in your water that cause hardness and stick to pipes, this basically makes them form tiny little crystals that are no longer have a positive or negative charge, which means that they're not going to stick to the plumbing. They're just going to flow straight through the system, and they'll no longer be a problem. And now, once again, taking a look at the iron content, this is another problem that is not really related to health problems, but it can clog up your plumbing, and it's a very annoying mineral to deal with. Now, iron is in a lot of the foods that we eat, like tomatoes, and it also constitutes a pretty big portion of the Earth's crust. So it's a very common mineral, but it's very annoying to have it in bore water. So as mentioned, what we found with our bore water is that it changed to a color that was almost similar to the color of this orange here, and we were pretty concerned because the water looked gross and it was leaving stains and just clogging up our different fixtures. So we knew we had to figure out some kind of solution, and what we basically found was that if we give the iron in our water enough time to oxidize, it forms into what's called a precipitate, or just solid particles that can then settle to the bottom. And so the solution ended up being really, really simple, in that after we filled our 10,000 litre water tank with water, we basically allowed a week or two for the water to settle, and that resulted in us having water with this level of clarity that is basically good to drink. So cheers to this. And this is basically the extent to which we treat our bore water. We run it through a filter jug for the purpose of drinking, just in case, but for cooking and for using around the home, it's not a problem at all. And I guess the downside of letting the water settle in our water tank is that there's going to be a residue down the bottom that is going to have to be cleaned up at some point in the future. But even when you're using rainwater on a farm, you also get silt forming on the bottom of the tank from all of the dust and other particles that settle on a home roof. So having iron in your bore water is really a minor problem that can be addressed through just simply allowing the water to settle. So of course, if you have an outrageous amount of iron in your bore water and you're trying to use it for irrigation, there are different solutions that are also outlined in the documents from the Department of Primary Industries. Like, for example, there's this complex gizmo here where you're adding lime to the water and then having large spray jets and a floating suction valve that's going to suck from the top, not the bottom. But in reality, if you're using water for irrigation purposes, what can be done is that the water can be added to a small pond. And then what happens there is that the percentage of iron is diluted by the other water in the pond. And of course, as the iron oxidizes, it sinks to the bottom of the pond, where the plants can convert it to nutrients and whatnot. And in that sense, you can use the water for all kinds of irrigation purposes. So what's probably the major issue with our bore water that we have discovered so far is the sodium absorption ratio. So what this means is basically there's a high amount of sodium, and the sodium can accumulate in the soil, and it can't be leached out by rainwater because it chemically binds with the clay particles, and that can result in some really nasty things happening. So what can happen with a high content of sodium in the water is that it gives the soil dispersive characteristics. And what that means is that instead of binding together, when water is added to the soil, it disperses and it can be easily washed out. Now, the cool thing about what we're using the water for is surface irrigation, which means that if we're irrigating to a depth of just a few centimeters, that is the extent to which we're going to have a sodicity problem. But the key thing to understand is that sodicity is only something that really occurs in disturbed soils. And this is something that took a really long time for me to figure out, and I even had to get in touch with an agronomist to talk specifically about sodicity and if it's going to be a problem for us. And this article is something that I can put a link to on the screen if any of you guys want to read about sodicity. But if we scroll down to the bottom, we actually realize that even though this is a problem that can be really, really scary, where sections of soil simply collapse in on themselves because there's tunneling erosion happening and you can't see it happening, all of these scary things tend to only happen in soils that are disturbed. And this is because nature has an amazing ability to restore balance where there is an imbalance. And what I found in this article is that if water can penetrate your soil to start with, that's going to begin microbial action, and that's going to work in conjunction with whatever vegetation is planted in the soil. And if there is a high level of sodium in the water, as we've got increasing levels of sodium that can be a concern, in our situation, that is actually unlikely to be a problem because we're not going to be tilling the soil, we're not going to be ripping up a crop and continuously watering that soil. Where we're using the water is simply to encourage vegetation growth, to prevent slopes of the mound from being eroded away. And now that's the cool thing. If we have the vegetation on that soil surface that's being irrigated all the time, what it does is the plant roots work in conjunction with the microbes, and they basically expel the excess sodium from the water, similarly to the way that humans sweat. So this problem is something that seemed really serious at first until we learned that we're not going to be messing with our soil, and nature will be able to maintain the balance on its own. And in the instance of growing a crop like sugarcane, for example, that does require tilling the soil in between crops, when sodium is involved, routine application of gypsum or lime will be required. There are resources out there like this video by Ag PhD, and you can also contact your local agricultural government agency to seek advice on application rates and to test the levels of sodium in the soil to see if they're becoming a concern or not. And of course, another method is to blend bore water with rainwater by adding it to a pond or a dam, in which case the level of sodium and any other annoying minerals will be reduced in concentration.